Hello, welcome to this channel. In this video, we are going to discuss about breadth first search. Breadth first search is a graph traversal algorithm used to explore and traverse a graph in a breadthward motion. It starts from specified source vertex and systematically visits all the vertices in the graph, moving level by level. In BFS, the algorithm visits all the vertices at the same level before moving onto the next level. It explores all the vertices adjacent to the current vertex before moving deeper into the graph. This characteristic makes BFS particularly useful for finding the shortest path between two vertices in an unweighted graph. The BFS algorithm utilizes a queue data structure to keep track of the vertices to be visited. It starts from in-queuing the source vertex and then repeatedly dequeues a vertex from the front of the queue, processes it in-queues its unvisited adjacent vertices, and marks the dequeued vertex as visited. This process continues until the queue becomes empty, indicating that all vertices have been visited. By following this breadth-first exploration strategy, BFS ensures that vertices closer to the source are visited before vertices that are further away. This property makes BFS an effective choice for problems where the shortest path or level-based traversal is required. Breadth first search has several applications across various fields. Here are some common applications of BFS. The first is shortest path finding. BFS is widely used to find the shortest path between two vertices in an unweighted graph. Since BFS traverses the graph level by level, the first time vertex is reached during the traversal. It guarantees that the path to that vertex is the shortest. The second is connectivity. BFS can determine if a graph is connected or not. By starting BFS from a specific vertex and checking if all vertices are visited, we can determine whether the graph is a single connected component or has multiple connected components. The third is minimum spanning tree. BFS can be employed to find the minimum spanning tree of a connected, undirected, and weighted graph. By modifying the algorithm slightly, we can construct an MST by visiting the graph in breadth-first manner and selecting the minimum weight edges at each point. The fourth is web crawling. BFS is used by search engines to crawl and index web pages. Starting from a seed URL, BFS is employed to explore the web graph by visiting linked pages, collecting data and indexing them. This approach ensures that web pages are discovered in a systematic and breadth-first manner. The fifth is social networking. BFS is utilized in a social network analysis to determine a relationship and connection between individuals. By treating the network as a graph, BFS can be applied to find friends' connection and explore the degrees of separation between individuals. The sixth is puzzle solving. BFS can be used to solve puzzles such as sliding tile puzzles or mazes. By representing the puzzle as a graph with each state as a vertex and valid moves as edges, BFS can be systematically explored the state space until a solution is found. The seventh is garbage collection. In programming, BFS can be used in garbage collection algorithm to trace and identify reachable objects. Starting from the root objects, BFS can be traverse object references and mark the objects that are still in use, allowing the garbage collector to reclaim memory occupied by unreachable objects. There are just few examples of numerous applications of BFS. The versatility and efficiency of BFS make it a fundamental algorithm in various domains ranging from computer science and data analysis to network exploration and problem solving. Thank you for joining me in this lecture on BFS. I hope you found the explanation and example helpful in understanding this algorithm. If you enjoyed this lecture and would like to stay updated with more educational content, don't forget to subscribe to my channel or follow my profile.